Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 18 in the series on section 3.6, Nonlinear Systems of Equations. So nonlinear systems are going to distinguish themselves from linear systems by having different cardinalities of solution sets. If I talk about a system like x plus y is equal to 4 and x minus y is equal to minus 4. Well, these are both going to be linear systems. There are no powers, there are no logs, there are no exponents. There's just single powers of the variables and times constants and added together. And so we could see that one would give me negative x plus 4, and the other would give me x minus 4. These two will only have one point of intersection because they have different slopes. But what if these were squares instead? Well, then these would be squares instead. And what I would actually have is the intersection of these two parabola, one going up, one going down. And this would have 2 points of intersection. So because nonlinear equations can be curved, we might actually have multiple places where they can intersect. And so nonlinear systems can have a great variety of numbers of possible intersections, that is to say, solutions to the systems of equations. So, true or false? This is false. They are not constrained to the same 3 possible outcomes that linear systems are. We still want to take some techniques from linear systems, though. For example, if I have a solution solved for a variable, then I can substitute that into the second use of that variable, because we're presupposing that these two sets of x's and y's are in fact the same coordinate xy. That's the implicit assumption in even creating the system at all, that the thing which satisfies them all will satisfy them all simultaneously. So if I square all this and FOIL it out, I could combine like terms and set it equal to 0. Factoring out this constant, we could now divide off this constant and set the reduced equation equal to 0. This factors as such to give me solutions when x is equal to minus 6 or when x is equal to minus 1. We can find the corresponding values for y by plugging this back into the first equation. Y would then be equal to negative 6 plus 7, or 1, and if x was equal to minus 1, y would be equal to positive 6. It's sometimes hard to graph the corresponding nonlinear equations on the graphing calculator, although it can be done by setting two different y's, one equal to, say, the positive square root and the negative square root when you solve for y. But a great tool to use for checking your work would be Desmos, because not only can you put in linear equations, you can put in nonlinear ones as well. And then we can really attach our study to this geometric idea of intersecting points. So I will try to accompany a picture like this along with this particular set of algebra, which has a correspondence, right? I mean, as we solve one, we find the points on the other. But I think this is a beautiful picture, and we should associate nonlinear systems with these kind of geometric intuitions like intersection. We can also use other techniques from solving systems of equations by hand. For example, I am able to subtract one equation from another, or add it times the constant minus 1, and in doing so, completely get rid of my x variable, in which case I now only have minus 7y is equal to 21. This tells me y is equal to negative 3. We could then take this information back to one of our nonlinear systems. For example, x squared minus 4 times minus 3 would be equal to 16, and thus we would get that x squared was in fact equal to plus or minus 2. So taking the combination of all these, we have the following possibilities: minus 2 minus 3, and 2 minus 3. You might notice that if I plug in minus 3 here, I'll be adding 9 to this side and repeating this collection of equations. So these are going to be our only two solutions. We could also use a graphing utility to demonstrate this fact. Here we have another situation where we might consider elimination as a good method. If I, for example, take this equation, multiply it by 7, and add that to the top equation, then I'll be taking 21y squared and adding it to 4y squared to get 25y squared. I'd be adding 7 times 44 to 92, which would give me 400. And 7x plus negative 7x would cancel. Now this equation can be easily solved for y, but what we're going to have to do is plug each one of these back into one of the equations here and solve for x. But notice when I plug in either of them, I'll be squaring them, and hence getting 16 when I plug that back in. This lets me know that I can really just worry about plugging in one of these sets of values. Then I would get, for example, 3 times 4 squared minus x squared is equal to 44, which could then be solved pretty easily. Now, since either one of these y values would have produced either one of these x values, we're actually going to have all 4 of the possible different combinations. If you plugged in 4y, it would give you plus 2 and also minus 2. If you plugged in negative 4y, it would give you plus 2 and also minus 2 as corresponding answers. I just mean it doesn't matter if you plug a plus or a minus here, you're still going to get 16. But we do need to list all 4 of these possible outcomes. For this next one, I suggest following a substitution approach. If we plug in 6 over x in wherever we see y in the first equation, we'll get the following. Now, squaring and then multiplying on both sides by x squared to clear denominators, this can be solved by making a variable substitution, clearing off that common factor of 4, and setting my terms equal to 0. Factoring and setting each term equal to 0, this gets me solutions when u is equal to 9 or when u is equal to 1. Hence where x squared is, which gives me 2 solutions for each of these. Now we would want to take all 4 of these and plug it back in to solve something for y. I think this would probably be your easiest point of entry for that. And you'll get, let's say for the positive 3, a y value of 2. For the negative 3, a negative 2. For the 1, we'll get a 6. And for the negative 1, we'll get a negative 6. Here is the graph of our system of equations, and we can correspond these with our answers. I think this next one might be better written in exponential form. This is saying if I have x to the 5, that's equal to y. And if I have x to the 8, that's equal to 8y. This bottom equation means that 1/8 of 8 to the 8 is equal to y, and now I can set these two equal to each other. That would give me that 1 over 8 x to the 8 was equal to x to the 5. This would tell me, multiplying on both sides by 8 and regrouping, which I could factor out x to the 5th, and finally recognizing that I have a difference of cubes, I'd get the following. Now this is an irreducible quadratic and will only have complex roots, so my only real roots coming from this equation are 0 and 2. And 0 also isn't an acceptable base of a logarithm. Bases must be positive real numbers. So that means that our only value that we get is 2. We could then go back and solve one of these for y. X to the 5th is equal to y, and so 2 to the 5th must be what y is equal to. That is 32. And so we have this as our only potential solution. Here we have a couple of word problems. If the sum of two numbers is 44 and their product is 420, we might solve this by first solving one equation for y, substituting that into the second equation for y, and after distributing and grouping like terms and moving our terms over to one side. And now notice that I am going to wind up solving for exactly the question we were asking. What two numbers multiply to be 420 and have a sum of 44? Scrolling down through this list, we would eventually find 14 and 30 as being two things which multiply to be 420 and have a sum of 44. This gives me solutions x equals 30 or 14, and if we were to plug those back into one of the equations for y, we would find y equals 14 or y equals 30. So since it really didn't matter what order we phrased this question in, which was x and y here when I constructed the sum of two numbers, this truly is just giving me one solution. The two numbers are 14 and 30. We don't need two ordinate pairs to tell me that. For number 8, it says a rectangular television has a length of 50 inches. If a TV has an area of 1200 inches squared, find the length and width of the television. So let's begin with a picture. We have this diagonal, and they tell us that that's 50. They also tell us that whatever the length and width are, we know that the area, which is 1200, is equal to length times width. And we also know from the Pythagorean theorem that length squared plus width squared should be equal to 50 squared. So solving one of these equations, for example, taking and solving for L in my second equation here by dividing by W, I might come up with plugging that into this equation, a single equation just now in terms of w, at which point this would give me the following. We're going to clear denominators and make a variable substitution and regroup like terms to get. I don't think I would try factoring this. I would just plug it into the quadratic equation to get the following, which of course was our width squared. When we're dealing with physical distances, only positive quantities make sense, and so we're going to have 40 here or 30 here. But if we look at what that would mean for L as 1200 divided by W, one would give me 30, and the other would give me L is equal to 40. And they established in the problem that length is greater than width, and so we would discard this set of solutions as being equivalent and just, not saying, like tilting the TV on its side or something like that. So we wind up with 30 for the width, 40 for the length. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.